You know, nature is an absolutely incredible engineer. It's had millions of years to perfect its designs. So when we humans want to build something tougher or stronger, honestly, the best place to start looking for ideas isn't always in a high-tech lab. It's right outside our door. So let's get into it.
Here is the big question, the puzzle that really gets materials scientists excited. Think about a seashell. It's mostly made of calcium carbonate, which is, for all intents and purposes, chalk. And you know how easily chalk snaps? Yet the shell itself, it's unbelievably tough. So what on earth is going on? The secret, it turns out, isn't about what it's made of, it's about how it's all put together. And that secret recipe has a name, Nacre. You might know it as mother of pearl. The best way to picture it is like a microscopic brick wall. You've got these tiny, brittle ceramic bricks, and they're all held together by this flexible, organic mortar. It's such a simple idea, but it's absolutely brilliant, and it's what gives nacre its amazing properties. So here's what we're going to cover. We'll start with Nature's toughest secret, then see how scientists are building their own version in the lab. We'll look at how they put it to the test, find out why the old math was wrong, and finally, see how this is paving the way for brand new super materials. All right, so what is it about this natural brick wall that's so special? Well, to really get it, we need to first understand two words that people mix up all the time in materials science: strength and toughness. Okay, so strength is all about resisting force. A ceramic plate is really strong, right? You can stack a lot on it. But toughness, that's about resisting a crack. You drop that strong plate and it shatters. It's strong, but it is not tough. Now think about a car tire. It's incredibly tough. You can whack it with a hammer and it just absorbs the blow. The absolute genius of nacre is that it is both strong and tough. And let me tell you, that combination is the holy grail in materials engineering. And that's exactly why nacre is such a superstar. It's 95% brittle chalk, but it's ridiculously tough. And here's how. When a tiny crack starts to form, it can't just slice right through. It hits that overlapping brick structure and is forced to take this long, winding zigzag path. It's like a maze for cracks. All that twisting and turning just sucks the energy right out of the crack, stopping it dead in its tracks. And that elegant solution is exactly what engineers want to copy. So, you see what nature did. The next big question is, can we actually copy it? Researchers decided to build their own version of nacre from scratch, using some pretty common materials to see if they could really nail down the physics of what makes it so tough. So for their bricks, they didn't use chalk, they picked thin sheets of polystyrene. Yeah, the same kind of stuff you'd find in a model airplane kit. It's stiff, it's brittle, a perfect stand-in. And for the mortar, they used a flexible polyurethane resin, which acts just like that tough, sticky protein holding a real seashell together. Now, this wasn't just slapped together. The process was super precise. First, they measured the exact properties of their polystyrene and polyurethane. Then, they brought in a CO2 laser to cut these beautiful, intricate hexagonal patterns into the polystyrene sheets. After that, they carefully stacked 6 layers, alternating the laser-cut sheets with the liquid resin. And finally, they put it all under pressure and let it cure for a solid week. And wow, just look at the detail here. Under the microscope, you can see those perfect hexagonal bricks. But look even closer. See those tiny little connections between them? Those bridges are so important. They aren't there for strength. They're just there to hold the whole delicate powder in place during assembly, making sure that brick wall structure is absolutely perfect. Okay, so they built it. But here's the thing about science. It's not enough to just make something. You have to prove that you understand why it works. And to do that, they came up with a brilliant plan to test their creation, not 1, not 2, but 3 different ways. This was their 3-point check, and it's fantastic. First, they went to the real world. They stuck their material in a machine and literally pulled it apart to measure its actual stiffness. Second, the digital world. They built an exact computer simulation, a digital twin, and did the same test virtually. And third, the theoretical world. They checked what the existing math formulas predicted the stiffness should be. And when I say digital twin, I don't mean some basic sketch. I mean, look at this thing. They put their sample under a microscope and modeled every single detail. They even included the tiny little bulge of melted plastic that the laser left behind. That level of detail was absolutely essential for an accurate simulation. So, the moment of truth. They ran the physical test and they got their number. The real-world stiffness was 1.221 gigapascals. That number became their ground truth, the benchmark.
So how did the simulation do? It predicted 1.21 gigapascals. I mean, that's an almost perfect match, off by only 1%. The physical and digital tests lined up. The experiment was a huge success. But what about the theory? This is where the story takes a really cool turn, because when they compared their real-world results to the predictions from the established scientific models, they didn't line up at all, not even close. It turns out the standard mathematical models that everyone had been using were just plain wrong. I mean, the most common one, the shear lag model, was off by a massive 31%. This wasn't a tiny rounding error. This pointed to a serious flaw in how scientists thought these amazing structures actually worked. I mean, you can see it plain as day right here in this table. The shear lag model, off by 31%, the Luce's model, off by 20%, the Pottewer and Beecher model got closer but still missed by 6%. Now, their super detailed computer simulation, the FEM, was nearly perfect, only off by 1%. But look at that bottom line. The new, simple model these researchers proposed, it was off by less than 1%. It was just as accurate as a supercomputer. So, what was their secret? Well, here's the crucial insight. All the old models made a big assumption to make the math easier. They assumed that the tiny gaps between the bricks, those little spaces filled with mortar left by the laser cut, were so small they didn't matter. They just ignored them. But it turns out, in the real world, those little gaps matter a lot. And this picture just shows you how clever their solution was. Instead of trying to treat the whole material as one uniform block, their new model breaks it down into different zones. It calculates the stiffness for the parts where 2 bricks overlap, the parts with only 1 brick, and, this is the key, it actually accounts for those non-reinforced gaps that are just filled with the weaker mortar. By adding up the contributions from each little zone, it got a near-perfect result. So you might be thinking, okay, they fixed a math problem. Big deal. Well, it is a huge deal, because having a simple, accurate, predictive model like this is basically a cheat code for designing new materials. It lets you skip years of painful trial and error in the lab. Remember, the polystyrene they used was just to prove the concept. But what happens when you use this same Nacre-Like design with some truly high-tech materials? Polystyrene has a stiffness of about 2.65 GPa. But a modern carbon foil? Try 600 GPa. We are talking about a performance leap of more than 200 times. And with this new model, you can now predict with incredible accuracy how that new super composite is going to behave. And this is what that looks like in practice. This graph is their new model, their new design tool, doing its job. It's predicting the stiffness of a future carbon epoxy composite. A designer can now use this formula and instantly see how changing the size of those hexagons will impact the final material. They can tune the design on a computer to squeeze out every last bit of performance before they even make anything. So when you boil it all down, what they've done is create a powerful shortcut. By looking at a seashell, carefully copying it in a lab, and fixing a fundamental flaw in the math, these researchers have given us a tool that's going to dramatically speed up our ability to design custom-built materials that are stiff, strong, and tough, just like nature's best. And it really makes you wonder, doesn't it? Mother of pearl is just one of nature's countless brilliant designs. You've got the structure of bone, the surface of a lotus leaf, the wings of a butterfly. What other incredible secrets are just hiding in plain sight, waiting for the right scientific model to finally crack their code?